Okay, so let's talk about algebraically finding inverse functions. Uh, so you have f, which takes an input and gives you an output. We want to undo everything, and we want to solve for to get back what we started with. So we have a function that goes like this, and we want to find one that takes us right back to where we started every time, no matter what, no matter what. So the way that we originally think about a function f is that the inputs we call x, and then the outputs we call y. So it makes sense to think of it in the original notation. Y is an output and x is an input, and f is the function. And the inverse function, well, you're a weirdo. F inverse takes a y and gives you an x. And that's, if you want to think of from the point of view that f is like the original function and f inverse is kind of a weirdo, then that's kind of how you think about it. The other point of view is you want to think about it from f inverse's perspective. Maybe f inverse thinks that it's the real function, and then f is the inverse of f inverse. Which is sort of equally valid. So if I want to think of these as being the inputs and these being the outputs, and then f, it's just if I switch everything around, then suddenly everything is kind of backwards. But if a lot of times the book asks for you to write it in this format. What is f inverse of x? So your answer has to have x's in it. So if I plug 4 into the f inverse function and I want it to spit out 2, what's the general function that does that? Well, here's sort of the process. So, sorry, I should be using function notation. So the instructions say we have a function f that behaves like this. So, so like the process is so we write down y is equal to f of x. So that's kind of the first step. So I'm solving problem A. That's kind of step 1. Step 2, we're going to change notation. Just because our final answer, we want to say what is f inverse of x. We want to be thinking about it from the other function's point of view. What used to be the output, they're switching roles. We want to think of, if we have an output of f, we want to think of that as an input for f inverse. So we swap x and y. And I want to sort of just remind ourselves to write down it's kind of we write something down in the original point of view, and maybe we sort of put a dividing line here. This was like step 1, step 2. I just write down y is every place where I used to have an x, and I write an x every place that I used to have a y. So that's kind of weird, but now from the point of view of f, we have y is equal to f of x. If we switch the roles of x and y, well, x is the, now if I switch the roles of x and y, then this is f inverse point of view, which says that for this equation, y is f of x, but for this equation, now y is, so if I switch the roles of x and y, then it's not, y is not f of x anymore. Now y is f inverse of x. So switching these is the same thing as doing this. So So I like to sort of, these steps are closely related, and that switching the notation around corresponds to, yeah, we're not in this world anymore. Now we're looking at everything. We flipped the notation, which means we're going backwards, which means y is now f inverse of x going forward. So we take what we did and then sure, the final answer is whatever that y is. So so divide the whole thing by 3. So remember, divide the whole thing by 3, which means that y is equal to x minus 2 divided by 3. So that's your answer to problem A. So yeah, so that's, it's kind of really worth emphasizing. These two things are not talking about the same notation anymore. It's like you've completely flipped you've renamed all the variables in this one step. And it's good to it's good to sort of know exactly where it is that you flip your perspective and what the implications are for, what do the variables mean? If I write down y is equal to f of x, then that means y is 3x plus 2. But if y is a variable that represents f inverse of x, that's the same relation with the roles x and y completely reversed. And f and f inverse, they are very closely related things, and you just swap the x's with the y's and use the same relation but with the variables reversed. And now we're describing the same ordered pairs but with the relations just completely backward. And then if I'm below this squiggly line, then all these x's and y's are describing the relationship y is equal to f inverse of x. All right, so that's the idea here. And something is actually, for C and D, I had to specify the domain, because if you look at these, you'll notice that we're squaring something, and we want to square either all positive numbers or we want to square all negative numbers. It's sort of a one-to-one issue. If you notice that I cut it right at the vertex, so that's interesting. We'll look at that a little bit more closely in a minute. So it's something I want you to be aware of. I think the MyLab tests are not quite this subtle, but this one is pretty straightforward. You'll probably see one like that. So part B, you will want to understand at least. So we have step 1, I write down y is equal to f of x, which means y is equal to 2x cubed minus 1. So from the function f's point of view, f takes an input that's called x and then gives you this output that it calls y, and it looks like this. And then for step 2, so the f point of view is here, the f inverse point of view. Most teachers don't require to say this. I don't require it, but it's really, I want you to understand what you're doing here. We're now in the point of view where it's like the two different Spider-Mans pointing at each other meme. It's Spider-Man and Spider-Man having an argument. It's like, no, you're the invertible function. You're doing the opposite of what I'm doing, and then vice versa. So it's really, like that. So from the f inverse's point of view, this y represents f of x, but now if I completely change the notation, if x and y are playing opposite roles, then suddenly this y in this equation represents f inverse of x. So it's kind of like that. And then, well, okay, if we can solve for y, then y is f inverse of x and we're done, but we haven't solved for y yet. So 2y cubed is equal to x plus 1. 1/2, multiply that on both sides to get 1/2 of x plus 1 is equal to y cubed. And then we take the cube root of both sides, which is the same as the 1/3 power. And so we get 1/2 x plus 1 to the 1/3. And that thing's also called f inverse of x. So you could use cube root notation, you could use the fractional exponent notation, the 1/3 power accomplishes exactly the same thing, cancels out the cubed on the y, and you get the final answer. So that was so I want, so I get my new point of view. I sort of can make a note to myself, what does that mean? Step 4, I solve for y, and then 5, I write down my final answer. Well, what does y represent? Well, I just said that y is f inverse of x, and that's what the question is asking for. All right, so C and D. I think we'll have to go to the other side here. I'll just leave it here. I'll just have to erase everything a little bit here. So notice that x squared, or x minus 1 squared, unless I restrict the domain, that's not going to be a one-to-one function. I have to make sure I don't get the same output twice. And this is a basic parabola that's been shifted 1 to the right. So to the right of 1 and to the left of 1 are two different sides of the parabola, but those two different functions should have two different inverse functions as well. So let's sort of explore that a little bit. Okay, so we have and I'm actually going to put the domain restriction. The domain restriction is actually one of the things that switches roles when you switch between x and y, actually. So here, this is f's point of view. And the f inverse point of view says not only is x equal to y minus 1 squared, but it's not x that's greater than or equal to 1. We know that y is going to have to be greater than or equal to 1. Everything about this xy relationship is reversed, including everything that used to be true about x is now true about y, because they're literally just completely mirror image over the y equals x line. It's completely swapping everything about them. So now that's also true, and then y is not f of x anymore. Y is now y is now f inverse of x. Yeah, okay, so we've got well, Well, this is a problem. We have to know which square root are we using. So it has to be one or the other. We don't know which one yet. Well, here's where this comes in. We know that y has to be bigger than or equal to 1. And how can that happen? Well, if we use minus here, when we plug in different x values, we'll get things that are smaller than 1 when x is like, 1 or 2. So here's so we can plug in all the different x values. And it's like if x equals 1, then y is equal to 0. And which is a contradiction. Which means we're happy with this one. So that's a little bit subtle, but it's kind of important. If they're being nice to you, they'll it's really easy to forget about the negative square root as a possibility. In this particular problem, the positive square root gives you the correct answer. But that's some food for thought. So if I do problem D, almost everything is the same, except for at the very beginning of the problem, we have the reverse. So let's sort of walk through that. And if you ever see that in another class, you'll understand where they're coming from. All right, so part C, that's what we got. All right, so what changes this if this is problem D? Yeah, problem C, x had to be positive, it had to be greater than or equal to 1 for the original function f, which means for the f inverse function, the y's have to be bigger than or equal to 1, which means that this negative square root didn't work because when you plug in x values, you get y's that aren't as big as they're supposed to be, but for plus, everything is fine. Now we're going to get kind of the opposite. So let's change it to problem D. So what changes? So if in problem D we have the same function, but we use the half of the function where we use a different half of the parabola defining another function that only works for x is less than or equal to 1. So the function f of x is x minus 1 squared, but x is less than or equal to 1. The inverse of this function with that domain, now we have that y has to be less than or equal to 1, or else we've made a mistake. Y has to be less than or equal to 1. We solve for y. Y has to be 1 and then plus the square root of x, or it could be y is 1 minus the square root of x. Either one of these could have been true. Well, because it's this question, question D instead of question C, what we need is we need y to be less than or equal to 1. So when x is equal to 1, this one's not good because then y is 2, but y was supposed to be less than or equal to 1. this one here, when x is 1, y is equal to 0. Now this one is good and the other one is bad. So a nice exercise, you really want to double check you know, you can graph them as pairs. So if you don't believe me, try graphing it. What was it? It was the plus. What's this one? Yeah. Something you might want to try. So the right half of this parabola is going to be this upper square root. And then the left half of the parabola is going to be the lower square root. So I can do a super duper quick sketch. X is bigger than or equal to 1. You get a parabola like this. And then 1 plus the square root of x. Here's the axis of symmetry. I've been doing green for this. For the other ones, so sure it'll look like this. It's like, oh yeah, that's really nice, right? And then the left half of the parabola, maybe I'll use blue and red for these. So the left half, so this function in blue is if x is less than or equal to 1 and f of x is x minus 1 squared, you get a blue parabola like this. Well, then maybe red for the other one. Well, what is the mirror image of the blue parabola? 1 minus the square root of x is kind of this weird looking thing like this, yeah. So this sideways parabola, the top and bottom halves of the sideways parabola are mirror images, respectively, of the right and left halves of the just the straight up and it's the upward opening parabola. So you can sort of, if you want to do this very slowly, you'll see it in a lot more detail. But that was a rough sketch of how this answer connects to the graphical explorations we did in the other section. So some good stuff to think about, some good things to practice. Connects to some things you've already seen, but what we're going to do is we're going to connect this to the exponential function. And so we're going to, because the exponential function is so important, we're going to slow it down and we're going to spend some time on that just by itself before we put all the pieces together in like sections 3 and 4. So, but yeah, that's it for 5.1. It's kind of a big theoretical section. It's a pretty big concept, but hopefully that helps.